All right, so we're going to look at a common type of problem that we face in power systems, which is that of power factor correction. So what we're referring to is a situation where we have something like this picture shown right here. So I have some sort of a load in this case, which is drawing some current, and that load's going to have some complex power associated with it. And I could say the complex power of that load is PL plus JQL. All right, so that load could have either a positive or a negative Q depending on whether or not I had a capacitor or inductor. Okay, so we have a source in this case with the voltage phasor V sub S, and that source is driving that load through some impedance that we call a transmission line. Now you'll notice, as I say here, an ideal transmission line should have no loss. In other words, the real situation that I would desire to have is that I have V sub S, and then I have a wire, and then I have a load over here, right? That's our ideal scenario. But the reality is that real wires and real elements that exist between this voltage source and this load have some kind of impedance. They naturally do. Okay? Now the source in these sorts of problems is the electric utility. And that electric utility needs to produce the complex power that is required by this load. And I say the complex power required by this load because it has to produce both the P and the Q to be able to do that. And that complex power basically comes from converting the primary energy that the utility buys into electricity. So that primary energy means either natural gas or coal or nuclear or solar, right? Ideally, this transmission line has no loss, but because it does have loss, that means that this current I sub S that the utility needs to provide to the load in order to be able to feed that load, that current will have losses in this transmission line. And I've written out the relationship here. The P value would be I squared R, and the Q value would be I squared times omega L, which is the magnitude of the inductive impedance. So ideally, we would want to minimize this, particularly the I squared R, which amounts to heat loss. All right, this I squared omega L is basically energy, magnetic field energy that is stored around in the magnetic field that exists around the wire. All right. Ideally, I'd like to minimize both of those things, particularly the heat losses. So how do I do that? Well, let's look at this example a little bit further. So if our load demands a complex power PL plus JQL, there are two components to this. QL, which is the reactive power, is the power that's required to create magnetic fields and inductors, and electric fields and capacitors. As we've said before, this is basically energy storage. So this guy here is the energy storage required just to make my load function. All right, so particularly usually if I have motors, I require this guy to be able to just function. PL, on the other hand, is the real power that represents the time average conversion of electrical energy into physical work. All right, so on average, basically at that load site, you are converting electricity into heat, right? Or light, or motion, or you're basically making electrons move around inside your computer. So there's always some sort of amount of physical work that's going on, and P sub L represents that. So the typical thing that we think about is that the P sub L part is really the most important part, because this is the thing that represents the real conversion of energy that's happening. The energy storage is the energy storage that just has to be there to be able to support that energy conversion. So one of the things we typically try to do is just try to reduce that Q sub L, and there's good ways to do that. So let's say we have this sort of a system right here. So what we have is a load that is absorbing, in this particular case, 10 kilowatts and 8 kilovars. Now because my Q is positive here, I know that my power triangle would look something like this, and I should be more careful in this case. Let's see, so he's going to be, my P will be here at 10, my Q will be almost as large here at 8, This guy, my S vector will point up. All right, so I see that my phi here is pretty large. Now I know that this is an inductive load, and the reason I know this is inductive is because I have a positive Q. Now, because complex power is equal to V times I conjugate, I can do a quick check real quick to see how much current is flowing through this line. So to do that, I say the magnitude of SL, which I call the apparent power, right? That would be 10,000 squared plus 8,000 squared square root. If I do that calculation, I end up getting 12.806 times 10 to the third, or I'm going to write it as kilovolt amperes. All right, because it's apparent power, I write it in volt amperes. So I take that value and I divide by the 250 to get the magnitude of the current. So essentially I just want to get the magnitude of the current in this case. I'm not worried about the whole phasor. So I see that the magnitude of the current works out to be 51.225 amps. Okay? All right. So that's what I have to start with. The question I have is, can I reduce that current if I do something to reduce the amount of reactive power that needs to be drawn from the utility over into that load? And I can do that. All right, so let's try an arrangement like what we have here. So what I've done is I've put a capacitor in parallel with this load. Okay? So with that, I can say that the total power is as is written here, right? So the total power, and just to be clear, let's draw this over. Let's say I have this scenario. So I'm saying that the total power going into these loads, this guy is a combination of L1 and C. It is his power that is S. Okay? So S has a power that is the power of the previous load plus this capacitor that I'm adding in. Okay? And I know in this case, because I've added a capacitor, I know that Q sub C is negative. Okay? And so what I've done is I've said, well, now the total reactive power is this. And just to be clear that the capacitor has a negative, the way I've written this here is I've said PL equals, or S equals PL plus JQL absolute value, to represent the fact that my existing load has a positive Q and that my capacitor has a negative Q value, right? So basically, in this case, I'm saying that QC is equal to the negative of the absolute value. I'm doing that on purpose, as we'll see as we go forward, right? Okay. So the idea here is if I choose a capacitor value whose magnitude of its reactive power is exactly equal to the magnitude of the reactive power that the load is currently absorbing, then what I can have from this relationship that we had before is if QC equals QL, if the magnitudes of those are equal to each other, then I get this relationship here where those two reactive power components balance each other. And the complex power is simply the real power. All right, what does this mean? Right, well, because of the relationship we have that says that complex power is equal to P plus JQ, and we write that as magnitude S cosine phi Z plus J magnitude S sine phi Z. Right? Clearly, if this thing is just equal to P, it's got to be the case that phi Z equals 0, so that the cosine is equal to 1 and the sine is equal to 0, and this goes away. For this reason, because the power factor is 1, we call this unity power factor. All right? So essentially what that means is if I were to draw the voltage and current phasors, voltage is here and current is here. So they are in phase with each other, meaning that the parallel combination of load 1 and the capacitor here effectively looks like just a single resistor now. As far as the utility is concerned, I turned that thing into just simply a resistor. Whereas this guy before was a resistor and an inductor in parallel with each other. The reality is there's a resistance, inductance, and capacitance, but I've made it now look like it's just a resistor. So the L and the C are balancing each other. Okay, so in this case, we say the load has unity power factor, and the load effectively now looks like it's simply a resistor. So let's look at this example problem. So in this case, I have SL equals 10 kilowatts plus J times 8 kilovars, and I put the capacitor in parallel with that. So I've identified that I need a capacitor, and I guess the magnitude of QL is 8 kVars. And just to be clear, the actual QL in this case, since it's positive, is just 8 kVar. So that means that I need to have a capacitor with negative 8 kVars, or I need a magnitude of Q sub C equal to 8 kVars. So there's two ways of looking at this. The critical relationship that we have that helps us with this, if we go back to the summary table for all of our power relationships, the critical value is that reactive power, which we know is always V I sine of phi z, can be written as V squared over the imaginary part of an impedance. Okay? So in this case, because I'm talking about a capacitor, the impedance I'm referring to is 1 over j omega c, or negative j over omega c. Right? Those are two equivalent statements. So I can write this two ways. I could say, the magnitude of Q sub c is equal to V squared divided by the magnitude of the imaginary part of the impedance. Or I can say Q sub C is equal to V squared over the imaginary part of the impedance, which is what I wrote up top. Okay, so the only reason I say that is I do things a little bit differently here. If I do the magnitude side, I say the magnitude has to be 8,000. In this case, because my voltage is 250 with an angle of 0, I say 250 squared divided by the magnitude of the impedance, so that becomes 1 over omega c. Everything in that relationship is positive. On this side, I say it's negative 8,000, right? I'm not doing the absolute values here. And this becomes on top 250 squared, so the same relationship as before. But on the bottom, I put the imaginary part of the impedance. So if I look at my impedance relationship, because I'm talking about a capacitor, I'm talking about something that is imaginary to begin with, but the imaginary part of that z is negative 1 over omega c. So we notice that the minus signs cancel each other in that relationship. Okay? So essentially, these two relationships are now the same. I just wanted to point that out because you got to be a little bit careful about these signs. In your results, you should never, when you're doing these problems, ever get a negative capacitor value or a negative inductor value. If you did, you probably got the signs wrong in terms of this step right here about whether you were looking at the absolute value or not. Okay, so what I have is 8,000 equals V squared times omega c. Right, so I basically just brought the 1 over omega c and upstairs and rearranged that. And we said the voltage was 250 volts RMS. Now we haven't been told what the frequency is, but I'm going to tell you right now. It's in the US, so that means I have a 60 hertz frequency. 2 pi 60 times c. So c equals, if I do that math right there, I will work out to 0.9 microfarads. Okay? So that's how big this capacitor needs to be. if that's the case, once I have that scenario, what I'm saying is effectively with that 0.9 microfarads, I've changed this problem now so that I have 10 kilowatts as I did before. I have 8 kilovars being absorbed by my load, but that 8 kVars is being supplied now by this capacitor I put in parallel, so that the combined complex power is only 10 kilowatts. That means that one thing that probably will confuse you a little bit, but the magnitude of that is simply just 10,000. And we say that that's in voltamps, right? So the magnitude of the complex power, which we call the apparent power, has units of voltamps. In this case, the voltamps and the kilowatts are the same. Or I should say the kilovolt amps and the kilowatts are the same. So if I want to know what's the current in this case, remember this is equal to VIS conjugate. So I can say that in this case, IL is the magnitude of IL, or sorry, the magnitude of IS, right? This guy's labeled as IS. The magnitude of that is 10,000 divided by 250, which works out to be 40 amps. Now, if you go back to the beginning of this, you'll see that when I did it initially without the capacitor, I had 51.225 amps. So I've got about 11 amp reduction here, so relatively significant. The big thing is the difference in power loss here in this transmission line. So the power loss in the transmission line previously with that 51.225 amps, if I calculate that power loss by saying I squared times R, so the R is 0.05, that works out to be about 131.2 watts. In other words, there's 131 watts of loss that is happening just simply to provide this guy with the power that he requires. Okay. In the new case, I have 40 squared times 0.05 because my current's gone down. That's only 80 watts. All right. Now, in the grand scheme of things, going down in that case, roughly about 50 watts isn't a huge value, but I'm talking about a pretty small system here. If I'm supplying, many gigawatts of power, this could become a pretty significant issue for me. All right. The key thing is significantly less power is wasted by the utility, by this guy. Less current needs to be sourced by V sub S, which means less loss in these lines, which basically means that less primary energy is required by the utility. In other words, less fuel is required by the utility to get you the 10 kilowatts that you need to do useful work. That's the key thing. The utility has to give you the power you require to do the useful work. All right. This ultimately requires less fuel if I can get the total power, or if I get the complex power down, all right, like we have in this case. I'm wasting less energy, so I require less fuel. Now, utilities do build like this. So just as an example of this, I took a rate structure in North Carolina, what they call large general service. So this would be for a big commercial building, like the buildings that you have uptown in Charlotte. All right. What they say in here is there's this line here about the average power factor in the month for the customer. So basically it says if the average monthly power factor of the customer's power requirements is less than 85%, the company can correct the integrated demand. There's a lot of words there. Basically what it says is if your power factor is less than 0.85, 85% or 0.85, what they'll do is they will multiply your bill by 0.85 divided by your actual power factor. So in this case, let's say I'm using an example. Let's say your power factor was 0.8. So what Duke is saying is they'll take your bill and they'll multiply your bill by 0.85 over 0.8 or 1.0625. So in other words, you'll pay about 6.25% more. Now you won't. This is for a large commercial customer who might pay tens of thousands of dollars a month. In which case, that 6.25% is pretty significant to the change in bill. And as we saw, it's pretty easy for a customer to get their power factor to be higher. And the way of doing that is to add a capacitor in parallel like what we have right here. or an inductor in parallel. Remember, if this load L1 over here, if this load was capacitive, we might want to put an inductor in parallel. All right, so let's summarize our process here. Got a couple of steps we want to think about. First, in these problems, our first step is to figure out the combined complex power of all the loads. So in this case, I only gave you L1, but I could give you L1, L2, L3, which is a bunch of loads in parallel. I'd want to find their combined complex power. Once I had that, I would want to determine how much Q is needed to make S equal to P. Or in some cases, to make I may not always be making the power factor unity. I might just be increasing the power factor, but I need to determine how much Q is needed to make the change happen. Basically, the question then becomes, if the load has a positive Q, I'll need to add negative Q, which means I'm adding a capacitor in parallel. If the load has a negative Q, then I'll have to add positive Q, which means I need an inductor in parallel. Right? So that's a critical step to determine whether I need a capacitor or an inductor. The third step is to use the reactive power relationship we have to determine the correct L or C. And that relationship, usually because we're adding stuff in parallel, usually is this V squared over the imaginary part of the impedance. All right, so there'll be a number of problems that you'll focus on that deal with this type of thing.